Hello, everyone. This is Matthew Thompson speaking. Welcome to our Between the Layers live virtual panel discussion. This is our kickoff for a new series from the Society of Plastics Engineers, Additive Manufacturing, and 3D Printing chapter. And so today's discussion will be additive manufacturing, materials and innovations for aerospace and defense. And so you can see our panelists, everybody's lined up for us. And, um, and our sponsor for today's event is AdMan. And then we have several co-producers. SPE, of course, is helping. And then Implement AM, powered by SPE, and 3D Natives, which is also part of SPE's umbrella. So let me go to my next slide. So thank you very much to our sponsor, AdMan, and Densmore is a sponsor for our additive manufacturing chapter, and they've graciously sponsored this kickoff event for our Between the Layers series. And so you can see their ad here. They're a shop for your engineering and 3D printing and precision machining, injection molding type of needs. So if you have any needs, reach out to densmoreinc.com. Let's see. Let me next turn it over to David Tucker. David, do you want to go ahead
Yes.
and introduce the Between the Layers series for everyone?
Yeah. So this is a production really of the Society of Plastics Engineers Technology Interest Group for Additive Manufacturing. It's a volunteer-based organization. Anyone can join, which is really great. And our mission is really to educate people on the uses of additive manufacturing in the industry. Now we have a bias toward plastics because we are mostly plastics engineers, but really anything that's additive manufacturing or digital manufacturing in the industry. And we're really trying to educate people, form community, get open discussions regarding the technology. So this is, as Matt was saying, this is the first of a quarterly series that we will be doing. It's called Between the Layers. Ray Shank from Diversified Plastics was the person who came up with the name. I think it's pretty good. And ultimately, what we want to do is have open conversations regarding technology with different people that are actually inside the industry, whether on the education side, on the application side, and and have a panel discussion and an open discussion. So if there's any questions, feel free to put them inside of the chat here. We will try to answer all of them. If we don't answer them, we will follow up with connect you to someone. Additionally, if you have any topics that you would like covered or any ideas for speakers or presentations, feel free to reach out to either Matt, myself, or Jay, or really anyone that's on the board of our technology interest group on like LinkedIn, and let us know what your ideas are. So as we said, this is the first of many. We plan on doing one regarding medical, one regarding the automotive vertical, and these different application spaces. So with that, I will hand it over to back to Matt to introduce the speakers and get the discussion going. Thanks.
Okay. Yep. Sounds good. Thank you, David. And yeah, so as he said, reach out to us. You see our URL here in the green box, speadditivemanufacturing.org. And we try to stay active on our LinkedIn page. So we're trying to get better, two-way communication with the industry and with our members for our chapter. So let me show a brief agenda. So of course, we just welcomed you guys to this event. And so our ideas for this are a virtual panel discussion. So we have a couple industry experts that I'm getting ready to introduce. And I've got a bunch of set topics that we'll discuss together. And then we want to save a lot of time for questions and answers. So put in your question, put in any comments in the chats, as soon as it pops in your head. We'll be watching that. And if we don't answer it, immediately, we're trying to save quite a bit of time at the end for open Q&A. So with that, I will introduce myself, give you guys a little introduction, and then I'll ask each of the panelists to introduce themselves just to get it started. So I'm Matthew Thompson. I'm with Toray Composite Materials America and their carbon fiber technical service group. And so Toray is a carbon fiber supplier for aerospace and defense industries, as well as industrial and sports and recreation, automotive type of applications. We're a carbon fiber material supplier. And so I've got previous experience with Boeing, and so aerospace and defense is kind of near and dear to my heart. And so that's why this kickoff panel discussion has this topic. And I've served with the SPE Additive Manufacturing chapter since like 2015, since close to the beginning of it. So with that, Ed, could you introduce yourself?
Sure. I apologize for my long career, but I'll just go in reverse chronological order if that's okay. I'm currently CEO and co-founder of Blue Sky Polymers, and we're focused on SLS and FDM printing of very high performance amorphous polymers. I'll say more about that during the discussion. I'm Emeritus Professor of Chemistry at University of North Carolina at Chapel Hill. In 2013, I am a co-founder of Carbon, and company is focused on both printers and materials. Carbon uses digital light projection for SLA printing of photopolymerized resins. I was recruited to the University of North Carolina in 1988 from the University of Connecticut, and I came down here to start a polymer program, and that has worked out wonderfully. My first faculty job was at University of Connecticut in 1972, and that was preceded by 2 postdocs, one at the Rijksuniversity of Groningen in the Netherlands, and a second one at UT Austin. My PhD is in polymer physical chemistry. I did that with Arthur Tobolsky at Princeton, and my undergraduate degree is in textile chemistry from Clemson University, and I look forward to chatting with all of you.
Thanks, Ed. Yes, very nice. Next, let's go over to Wout. Wout de Bakker, could you introduce yourself, please?
Yes, good afternoon, everyone. My name is Wout de Bakker. I'm an assistant professor at the University of South Carolina. I've been here since 2014, since when we started the Aerospace Engineering graduate program. And from during that, I've developed over 15 different 3D printers in all varieties of the technology from involving plastics. So either they are thermoset and thermoplastic plastics. We've published over 10 different patents on these technologies, and since then, I've also been the teacher for the aircraft design courses and senior design courses in our aerospace engineering program, where we've had a very large growth, and now with an incoming class of about 120 different students. Before I came to the university, I had a background in composite simulation and analysis, so we've built computer software that can do all sorts of fracture mechanics and computer-aided analysis of composites. So that's where my passion lies. My passion lies in aircraft design, machine design, and manufacturing automation, and combining that with composites, typically thermoplastics, thermosets, and continuous fiber additive manufacturing. Recently, our work has been more on the urban air mobility and advanced air mobility side, where we've been looking at applying these technologies and simulation tools to the emerging markets. Thank you.
Okay, thank you, Wout. And then last but not least, Victor, could you introduce yourself, please?
Absolutely, and apologies if I get booted here, as I just did a minute ago, but managed to come right back on time. Yeah, so my name is Victor Jaker. Welcome, everybody. Looking forward to a good discussion. I've been with, actually, my current role, I should say, is Manager of Technology Development for FDM within Stratasys Inc., which is the largest and one of the oldest additive manufacturing companies in the world, the inventors of FDM technology, for example. And in my current role, I oversee materials engineers, mechanical engineers, designers, and control specialists who are developing kind of our next gen materials and technology for FDM, in particular to serve mid to large format printing in the aerospace, automotive, and defense industries, but to some smaller extents into other industries as well, focusing a lot on materials with elevated mechanical properties, short fiber composites, and materials, of course, that meet flame, smoke, and toxicity specs for aerospace and rail. Been in this role currently about 13 years. Prior to that, prior to a management role rather, I was a materials engineer here, formulating, working on all the processes upstream of making FDM filaments and compounds, including with twin screw compounding, single screw extrusion, and all the other kind of upstream and downstream processes there. So very familiar with kind of the industrial plastics processing side of things that is necessary to get to the point of 3D printed parts. What else? My academic background is master's in polymer engineering from Lehigh University and a bachelor's degree in material science and engineering from the University of Minnesota. I think that's maybe all for now.
Okay, very good. Thank you, Victor. Thank you, everybody. So to kind of give a little bit more of a personal item or two, there's a bunch of plastics, of course. So this is a Society of Plastics Engineers event. So typically an event like this, we ask people, what's your favorite plastic? And so I'm curious what your answer is on that. And also let me know, what's your favorite additive manufacturing modality, we'll call it, process or type of printer or a specific printer if you have something in mind. We'll switch it up. Woot, what do you think? Favorite plastic, favorite printer or process?
Well, I'm previous to the education point of view here. So what I'm looking for when I think of favorite plastic is how did we educate as many people as possible using the technologies that we have. And in that perspective, as an educator, fused filament fabrication, fused deposition modeling has really opened up the plastic worlds to a lot of people, including the polymer PLA, which we know as an engineering standpoint doesn't have a whole lot of direct applications. However, from a prototyping and from a learning and from an involvement point of view, PLA, I think, has really changed the world for a lot of people. So that's my answer.
Very good. And it's got the sustainability angle, coming from a natural material. Okay, Ed, what do you think? Favorite plastic, favorite type of printer?
At the moment, my favorite polymer is a Torlon-like polyamic amidimide material. It's an amorphous polymer that nobody else in the world can print, and we're printing this. And I wanted to make it printer agnostic, having gone through the experience with carbon, where you had to build a printer for the resin and vice versa. And I'm essentially using a kit from Centratech that we outfitted with a CO2 laser and have been able to print as high as 300 degrees centigrade. So I'm not your typical printing person.
Hey, no, that's awesome. I think we just covered the bounds for the 3D printing world. Victor, what about you?
I'll cut right in the middle of that, I guess, in terms of properties and thermal resistance. One of the first commercialization projects I worked on at Stratasys here back in about 2013 or 14 was commercialization of Ultem 1010 polyether imide. So that material class, generally speaking, has been a very successful one for us. Partnership with the manufacturer as well as with all of our other customer partners to really get deep into aerospace because of that materials properties, kind of ticking most of the boxes, even as a 3D printed part for aerospace requirements. And again, as that kind of formative experience for me in my career working with that material, I'd say I like that material. I'd hesitate to say I have a connection to it, but at this point I probably do, since I've worked with it for over a decade. And as far as printers go, our 400 MC, it's an old model that's since been discontinued, but that's another one kind of that brings me some nostalgia. So Ultem for me.
Okay, very good. Thank you, Victor. Yep, makes sense. Okay, So I wanted to kind of set the stage. And so our title for our discussion is Additive Manufacturing, Materials and Innovation for Aerospace and Defense. So it's kind of a long title. It kind of tells you what we're going to talk about. But kind of to set the stage, we wanted to talk about materials and processes and then where all that goes. And so Ed, if you could set the stage for us for materials, what materials are currently being used in additive manufacturing, and then those specifically for this aerospace and defense market area. That if it's high performance to weight ratio, that's aerospace and defense, usually wants the performance and they're willing to pay for it. And so then you get to tinker around with the high performance, things, plastics and composites. So could you kind of set the stage for us for that?
Sure, I'm happy to do that, Matthew. And let me use that slide on the polymer pyramid in order to put things into an extremely general context. I think most of you have seen this before. We're looking at it at low resolution. There are commodity polymers at the bottom, like polyethylene, polypropylene, in the semicrystalline side of the pyramid, and things like polystyrene on the left-hand side of the material. So semicrystalline on the right and amorphous on the left. You can view the amorphous material essentially as a quenched polymer melt with no structure whatsoever. And at low resolution, the semicrystalline materials can be viewed as crystallites embedded in that amorphous matrix, providing a reinforcement of sorts and physical cross-linking of the material. The properties of polymers in this pyramid increase from the bottom to the top, and along with that increase in say maximum use temperature, it basically parallels the glass transition temperature of the polymers. Examples of well, I would say that today, aerospace and defense is virtually exclusively using semicrystalline polymers. There is an exception, which was alluded to just a few minutes ago, but I'll come back to that. Those examples include polyether ketones, PEEK, and polyaryl ether ketones, PAKE. The exception would be Victor's Ultem, essentially a polyether imide, which can be FDM printed with variable difficulty. To me, high performance polymers and high temperature means exploiting the excellent fluid stability of materials, and with really robust mechanical properties, 100 megapascal, tensile strength of 15,000 psi if you're in those units. High maximum use temperature, I'd say, with TGs above 250 centigrade, that's 480 Fahrenheit. So that materials with those kinds of properties in aerospace and defense can begin to replace metals in structural applications. Currently, really high performance amorphous polymers are inaccessible to aerospace and defense. And I want to talk more about that later on. We're trying to change that at Blue Sky Polymers, showing you how you can, in fact, FDM and SLS print this category of polymers.
Okay, man, that's excellent. That's excellent. That's very comprehensive. Like you said, yeah, we'll talk some more. Okay, let me go back up here. And so, I just mentioned, we're going to talk materials and processes. SBE, I feel like is a lot of materials focused folks. And so, I typically would refer to myself as a plastics person or a composites person. But in general, materials no good without a process to make something, with it, something useful. And so in this aerospace and defense world, a lot of times there's raw materials and intermediate materials and such, and then there's a lot of processing along the way. So Woot, let me go to you. Could you set the stage for us on what types of processes for additive manufacturing are out there, current states, and then also any trends that you're seeing or any future directions that you're seeing, just kind of just to set the stage to get us going?
Absolutely. So when you're looking at the different processes for additive manufacturing, there's two ways of really categorizing it, the types of processes that you can use. One of them is based on the process itself, where we look at the type of equipment that's needed to make a part. The other one is looking at the materials that you're using. So we're in the Society of Plastics Engineering event, so of course a lot of us are familiar with the thermoplastics, polymers and resins. But additional methods of additive manufacturing, including metal powders, ceramic powders, or even composite type processes, which include a variety of plastics within those composites. So if you're looking at the different methods that are existing, SLA, direct laser projection, clip, material jetting, are all really applicable to photopolymer resins. And when we're looking at the polymer size, the thermoplastic polymers, where we remelt and resolidify, typical processes include FDM, fused filament fabrication or fused deposition modeling, selective laser sintering, multi-jet fusion. Another way of looking at it is based on the process. So looking at what goes into the printer and how the printer processes the material. So if you're looking at the most common one out there is probably extrusion-based processes, again, looking at FFF or FDM, or photopolymerization processes, SLA, stereolithography, direct laser processing and projection. Binder jetting is a very common one as well. But if you really want to go broad, additive manufacturing is also excluding or including parts that include composite processes like automated fiber placement, continuous fiber additive manufacturing, and if you want to go really daring, may upset some people here, by looking at filament winding or hand layup and hand spray up as a additive manufacturing process. So what are the trends that we see on these processes? Well, we're looking here, for example, at the composite side. The advanced composites field is really developing a lot of these additive manufacturing processes because of the high entry to the market and the cost that is required to get the equipment to where it needs to be. Now, once it has been brought into the aerospace world, we see a lot of applications in other fields. In particular, the additive manufacturing through automated fiber placement or automated tape plating is really gaining a lot of traction, also on the non-aerospace side, and in the efficiency of composite part manufacturing. It's very hard to come even close to other processes. For metals and polymers, the trend is to integrate a lot of more traditional processes into the workflow, looking at hybrid processing or hybrid manufacturing methods, combining both subtractive and additive methods and different types of additives in one setup. And throughout all of this, a lot of trends include the additives and inclusions that are done on the material development, right? So there's a lot of material development happening to allow us to print better, print faster, get better layer adhesion on top of the software for simulation and analysis of the printed parts.
Very nice. Very nice, folks. Yeah, wow. Very comprehensive also. You know, you mentioned that the composites, aerospace composites industry, is additive. My background's, I did 2 years with Boeing Research and Technology in their additive manufacturing 3D printing research group. And that's what got me into this additive manufacturing world. And then now I've been with Toray for 7 years, and Toray's, carbon fiber supplier. And so, yeah, our materials go into AFP and automated tape laying, like you mentioned. And that was one of the comments I got early on when I joined over to Toray. These AFP and things, that is additive. You're building a part layer by layer. There's a lot of crossover there, and there's a lot of mutual learning, I think. And I'm curious, yeah, what the future may hold. Like you mentioned, AFPs being used, all kinds of different high performance, applications. And, there's this world of continuous fiber 3D printing, where they might play together. And so let me save that one. I think I'll ask you that one again, but just to keep setting the stage. Victor, you mentioned that your current role is the manager for the FDM Technology Development Group at Stratasys. And so you already mentioned, yeah, your favorite plastic, is Baltim. I know you can't get into anything proprietary, but just curious, what are some of your high level thoughts as far as what the future may hold for materials, equipment, software, or one or two trends that you're seeing for the future for within the FDM world?
I guess clarify within FDM or like FDM for aerospace, because they're maybe not exactly quite the same.
You pick.
I guess I'll pick aerospace.
Yeah.
So
Okay.
two kind of trends and directions. So the
Sure.
first trend is definitely going to be a continuation in trying to elevate the mechanical properties of materials generally. So firstly, that's going to be trending further and further toward isotropic part properties as much as that's possible. And there is actually, this is where it gets proprietary, but that's actually where there is still quite a bit of headroom. It just, requires some increased complexity of the whole process overall, really, with the same materials that exist today. And then one of the other trends that we're seeing is a bit less exciting than increased material properties, or I forgot to mention short fiber and continuous fiber composites. That's definitely something you see out there that more and more you'll see integrated into FDM generally. But the other trend that is not so exciting, but ironically is the more important one in terms of broader adoption, is going to be reliability and reliable part properties. So regardless of what those properties are, the aerospace industry in particular, but even other industries that are in production environment, want to know that what they're going to get out the other end of their AM process is what they expected. Whether that is something that is some isotropic polyimide type material with amazing physical and thermal and chemical properties, or whether that's something that is some polypropylene blend or something for the automotive industry. Being able to trust the process, being able to know without having to destructively test some fraction of every batch of parts you make, for example, is a big trend we're going into. So basically, it's that overall process of it's basically being able to trust the parts and trust the process. And then more increasingly, you'll see this will be tied to software where we gather more and more data, but then use that data to actually interpret what's been going on in the machine, where maybe some improvements need to be made. And then there's a whole other parallel path of quality control, documentation, et cetera, as well, that also needs to be included in there, which is pretty standard for aerospace and actually the medical industry as well.
Okay. Yeah, no, that makes sense. Yeah, I appreciate that. Okay. That was kind of setting our stage. Let's see. Victor, I'll keep with you here as we keep moving forward. So Stratasys, you mentioned, it was one of the first commercialized additive manufacturing 3D printing companies, and it was founded in 1989, so it's been around 35 years. And you guys have been in like the top 2 3D printing companies in the world pretty much that whole time. So I won't talk about mergers and acquisitions and the business side of things so much, but what are your thoughts for an additive manufacturing equipment and material provider? It seems like you guys are providing everything you need. So do you think that's important for additive manufacturing?
It is important, and I think it will continue to be important for some time, to the extent that many very detailed aspects of how the process, the structure, process, property relationships of the material and the hardware are still being fully fleshed out. I think a lot of people have very good general ideas of how that's going on. We do too. But to the extent that there aren't textbooks and classes that really dig into all the minutia of this the way that other more conventional manufacturing processes have. I think it's going to be still pretty important to have that OEM that, if not provides all of those services and products, provides that expertise. At the same time, we are learning that going into manufacturing, we do need to relinquish some control over some of these things with increasing requests for, access to some of our software and algorithms, as well as access to use non-proprietary materials on our systems for development or research purposes, or quite honestly, even for lower cost. And that's kind of the balance that we're dealing with now, is sort of yielding to those demands of the manufacturing customer and the researcher, while, as I said, trying our best to provide the best product, being that we do have the most data and information and history to try to put together into a coherent package for people. Hopefully that answered your question.
Mm-hmm. No, that's good. Yeah, I appreciate that. I see a good question from the chats already. And so, again, folks, as you're thinking of good questions or comments, or if you disagree with us, tell us. Anything that's said, we would like the interaction. But Cheryl mentioned, what are some actual examples of aerospace parts made with additive manufacturing today, within the last 5 years or so. And so, I'll start. So I mentioned I had previous experience with Boeing Research and Technology, and we were in the research group, and that was always a challenge, even within the organization, finding the good, application areas, where's the sweet spots for any technology, any material, you got to find the sweet spots. And so I'll give one example, and it's certainly not within, just within the last 5 years, but it's definitely, ongoing, is environmental control ducts and for air ducts. For, in this case, it was fighter jets in the defense world, but also I think in some of the other defense applications, aircraft, and maybe commercial side. But there was great parts. It was the F-18 fighter jets, and the way the story was described to me, this is back in the 90s. That was identified for nylon SLS printing. The primary structure of the aircraft, of the jet in this case, of course, is one of the first things that gets designed, and then they're designing all the avionics and the control systems, and then the environmental control system, the air ducts, are kind of the last thing, and they ended up having very weird paths, kind of snaking their way through the structure. And so back in like the 90s, they were able to take, I think it was 32 parts that used to all have to be joined together in there. And then the SLS printed 2 parts, and you kind of snake it in there, and there's just one little joint. And so I think that's an ongoing application area. I'll put that one to the panel. Ed or Woods or Victor, you have one or any good examples of aerospace or defense application, any parts for additive manufacturing 3D printing?
Yeah, ducting and clips are big ones. They're not they're maybe not the sexiest applications, but there's lots of places where that's useful. So and in aerospace, or sorry, in defense aerospace as well as commercial aerospace, I guess it's not quite 5 years ago, but we have parts flying via Lockheed Martin on the Orion spacecraft, as well as recently there was a press release that came out that some of our Antero materials, in partnership with a few aerospace companies, are actually going to be going to the moon as part of one of the upcoming missions, specifically a PEKK material with tungsten loaded in it to try to test effects of radiation shielding.
Very nice. Okay.
I'll add to that.
Sure.
One of the big parts of the aerospace world is not just what flies, but also what happens on the ground, right? So a lot of us are focusing on getting parts qualified to fly, getting them certified onto the aircraft. But there's a lot of use of additive manufacturing in just the fixturing and the rigging of the parts on the ground or during layup and installation. So those requirements there are quite a bit less stringent. Now, if you want to look at flying parts, there's a very big history on the ceramics additive and metal additive side, in particular with the titanium additive manufacturing in the use of turbine blades of aircraft engines. It's probably the one that has had the longest history on the aircraft because of the intricate channels that are required during the production and the cooling of those vanes. So that's my 2 cents on that topic.
Yep, no, that's excellent. Yeah, and you know, I'm here in Decatur, Alabama, and Huntsville, Alabama is kind of Rocket City, USA, and so I see a lot of metal additive manufacturing still for rocket nozzles, and like you said, for internal cooling and you know, moving fuel if you need to here and there. So yeah, that's an important area. You know, I was seeing a lot in the you know, most of the trade shows I go to now are composites focused, and I see a lot of the additive manufacturing folks are at the exhibit halls, you know, showing how to make tooling and molds to make composite parts for aerospace. So the big pellet fed, you know, systems, BAM, Cincinnati BAM system was one of the first, and then Thermwood and Ingersoll, I think. There's a whole bunch now, but yeah, that's a good example. Let me switch over for a question for you, Ed. And so I appreciate you describing your career. And so I had the chance to take a look at it. We hadn't met before this panel, but your career has been quite impressive. And so, like you mentioned, you've been in academia, you know, for most of that, and you had a endowed chair position and chaired a couple of departments at the university, and also some fellow positions and visiting faculty positions. And then you mentioned in 2013 you were part of the co-founding team that came up with Carbon 3D with your UNC colleague Joe DeSimone and others. And so could you comment on kind of what led to that, and you know, why did you guys spin that off into a company?
Yeah, that's in some ways it's a fairy tale, actually. We had founded another company, and Joe and I and we had this theoretical physicist, Alex Ermoshkin, who was working for the other company, and basically said one day, I'd like to build well, actually his son, who was a real genius kid, asked his dad if he could buy a 3D printer, and his dad said, look, why don't we build a 3D printer? And that's really how this started. That Alex Ermoshkin was certain that he could build a better printer than anything out there, and we all agreed that he could do that, but there was no IP. And basically, Alex looked at all the existing IP and came up with this idea that maybe we could exploit the fact that oxygen inhibits free radical polymerization, and the rest is more or less history. We had an oxygen permeable window, we put resin in there, and when you photopolymerize, it doesn't harden at the window, and so it's very easy to move up. You can almost go continuously and print. So it became a very rapid method for printing. And, you know, we were just toying around with it, built the first printer out of cardboard, and essentially went to Palo Alto and started talking to VCs, and they were so impressed they wouldn't let us leave until we took money from them. And so it really became a fairy tale. And when somebody invests, everybody else wants to invest, and it just exploded. And so it was interesting from an economic point of view. We were able to surf the hype of 3D printing and fast 3D printing, and at the same time, not only designing a printer and engineering that up, having to make materials that really made a difference. And one distinct advantage we had, in addition to typical kinds of materials, was to make very soft materials that could be printed into unique types of matrices, so that not only you have the elasticity of the material itself, then you have the structural dimensions of the matrix that you print, and you can then design things that are unique from a mechanical point of view. I think that Adidas joined us and we made 3D printing soles. And I mean, that sounds it really, I thought at the time was a marketing gimmick, but now we've designed matrices that give you a directional thrust after you compress something. And so it adds to the running if you're a runner, and then using these foam replacements in helmets, then you start to do idiosyncratic things, which is really the unique aspect of 3D printing, in my opinion, is to do something that is person specific. And we do that in foams for helmets and different types of things like that. And of course, we're now heavily moving into dental applications where that's entirely idiosyncratic. So it was an unusual journey. I think most startups don't have that type of success, and I'm witnessing it here with Blue Sky Polymers. So I've seen both sides.
Very good. You know, you make a good point. You know, I remember seeing the 3D printed shoe soles also and thinking that was kind of a gimmick, but they look really cool. And I still don't own any. I still that's on my wish list. But you know, you make a good point. You know, additive manufacturing world, we try to say that complexity is free. It's not necessarily free. You have to be able to design with it and do something and all that good stuff. But that is a nice you know, bonus advantage for additive manufacturing is, can we design structures that, you know, you push down and it gives you a forward thrust and those kind of things. And so yeah, you got to do something, and then maybe these cool applications come out. Yeah. Well, let me keep the floor with you, Ed. So you've mentioned a couple times your latest startup there, Blue Sky Polymers. Could you describe what you guys are up to?
Yes, I'd like to do with that with the help of a couple of more slides.
Cool. Go ahead.
I want to acknowledge our CTO, Theo Dingemans, who actually was a PhD student of mine, who then spent time at NASA. And at NASA, they were working on something called the X-33 to replace the space shuttle. They wanted to build a new version of the space shuttle, and they wanted to have the fuel tanks on the inside. And to do that, Theo needed to make a composite fuel tank that could go down to, you know, minus 250 or so centigrade, back up multiple times, cryogenic, hot, back and forth. And he did this by making an oligomer based on a liquid crystal polymer called Vectra that was made by Celanese. And he, instead of making a high molecular weight polymer, he made a low molecular weight oligomer and put reactive in groups on that oligomer. And when you put that together and you make a composite with carbon fiber, it's fantastic. In part because the coefficient of thermal expansion of the liquid crystal polymer is essentially identical with that of carbon fiber. So you can cycle it in temperature without having any degradation. And so we started to think, well, maybe this could be a generic way of making intractable, hard to process polymers more tractable, make oligomers from them. And let's see what's on the next slide, Matthew.
Sure.
Yeah, so we said, you know, why can't we do this with anything? And we simply make an oligomer, terminate it with these reactive in groups, and those in groups are thermally activated. And so when you heat that up, you can either chain extend depending on the temperature and get to a high molecular weight polymer, or you can get to a 3D cross-link network. And by working with an oligomer, before you do chain extension, you have a very low viscosity. So you can do things that you can't do with high molecular weight polymers. And this is when we realized that, gee, we can take this idea and move to the left side of the polymer pyramid and start making some of these very high performance polymers accessible. Thanks. I mean, this is a sort of a superficial summary of where things are. On the right-hand side, you can see that you can FDM, PEEK, and PESU, and ULTEM, although ULTEM is an amorphous polymer, Victor's favorite. But we're able now to print materials on the left-hand side of this pyramid by going through this reactive oligomer route. And there are advantages. Not only is it processable, we're doing SLS and FDM of these materials. Because it's an oligomer, the weld line during the printing is really fantastic because the small molecules can diffuse across and give you an ultra strong weld line. And so we're seeing isotropic properties coming out of these materials. So we're very excited about moving into this left-hand side of the pyramid and making everything accessible to 3D printing. And hopefully this will have an impact on aerospace and FDM. And we see that we've got a lot of customer pull now, even though we're focused entirely on making the materials and scaling those up and making them available to customers.
Okay. Well, cool. I mean, very interesting stuff, Ed. I appreciate you describing that for us. I think it's pertinent to our conversation today. Like I mentioned earlier, aerospace and defense, we typically are looking for the highest performance stuff, and you know, you have to be able to make a part out of it. So, like you said, some of these materials are extremely hard to process. Torline, you mentioned.
Sure.
You know. I think typically Torline, you have a billet and you machine it out. You know, it's the typical process, or you can process it kind of in a liquid format, but then the post cure, if you were trying to do the imidization, takes, what is it, days,
weeks,
weeks to make a part. So yeah, it's crazy. So
another advantage of those reactive in groups that we're currently using is that you can recycle the material endlessly because they just don't go off and nothing changes in the unused part of the printer bed. So from a financial point of view, that begins to become significant.
Okay. Oh, cool. Yeah. Well, anybody interested, of course, reach out to Ed, but I'm very curious. Yeah, we'll have to keep our eyes on this.
Thanks.
Thank you, Ed. Let's see. So we're over 3/4 of the way through our hour, and so again, I keep promoting the chat. So you know, the only way that we can interact with you guys, if you have questions and stuff, is through that chat. So let us know. Otherwise, we'll keep talking. I got all kinds of questions that we won't have time for. But you know, anything that you want to learn from our panel of experts here, just let us know. Any questions? So let me move over. So Woot, you know, we kind of prefaced it earlier, and I'll just kind of give you a question again. That's my personal interest is continuous fiber reinforcement. And so we talked earlier about AFP and then continuous fiber additive manufacturing. So if you could tell us, you know, are those two different things, or are they the same thing, or you know, and then if they're two different things, you know, what are you seeing there? If those are synergistic or play together in some different ways.
So kind of tying it back to the aerospace realm of things, right? So when we're looking at the aerospace manufacturing, a big interest is, you know, how do we get the composite benefits through an additive manufacturing process, right? And it started all with a hand layup process or a spray layup process. And now we're going into automation of that process through automated fiber placement or filament winding and then automated tape placing. Now, that worked really well for the very large structures. Like the prime example there, the Boeing 787, the A350, they have large parts of the aircraft completely made out of automated fiber placement technology. And they are talking deposition rates of several pounds per hour, right? So it goes really quickly. They have to bake it out in a massive autoclave at the end of that. So how do we tie that into parts that are smaller or parts that use different processes? So here at USC and several other research groups throughout the world have been developing these continuous fiber additive manufacturing processes. And depending on the group, they've done it in a slightly different way or a slightly unique way. Some using photopolymers, some using thermoplastics, some using thermosets. Here at USC, we've developed a variety of different equipment related to extrusion-based technologies, spray-based technologies, continuous fiber-based with both epoxy and thermoplastics. And one of the main challenges that we saw here, or the main similarities really between what's already done in AFP and what's emerging now on the continuous fiber side, is that the same challenges you have on the AFP side, you have them on the continuous fiber side. So the continuous fiber AM side. So it is an automation process. It requires capital equipment. The scale is a little bit smaller, but it has the same amount of axes. Oftentimes a 6-axis or a 7-axis or an 8-axis setup is what's needed to do proper continuous fiber reinforced additive manufacturing. And that has a barrier to entry, right? It has a cost entry. It has a software complexity barrier to entry. It has a learning point from an operator's point of view. And it has an analysis challenge, right? So how do you analyze these parts? They are oftentimes no longer flat or plate-like structures. They are often 3D lattices or very complex geometries that require, as we heard earlier, an interesting way of analysis so that we can get additional benefits like the thrust from compression. So the complexities are similar between the large scale. However, the difference is scaling it down. The cost doesn't change too much, but the complexity that you can get out of it is very similar. So what is the hardest part here is making parts that are smaller or using the continuous fiber technology to make smaller parts that still pay for themselves on the aircraft, because again, the cost per pound is typically higher than what you see for a continuous fiber AFP, for example. So this is, I think this covers both similarities and differences where, we see that, again, the complexity is similar, but the cost per part of the laydown rates is very different. And justifying that on the process is important.
Okay. Yeah, I appreciate that. And man, it's hard. I have basically zero knowledge on like designing composite parts and things, and so I just can't imagine trying to design a part and you have, like you mentioned, at least 6 degrees of freedom, maybe more. You can put the fiber in the direction you want it and all that good stuff. So it gets super complex, but the performance, could be awesome as well. So okay. Thank you, Woot. And so let me pass it over again to you, Victor. Maybe one last one or two more questions, 3 questions if we have time. But Victor, I was going to ask you about, we talked a lot about these pushing the boundaries, to be able to use these really super high performance materials. And then Woot just described, using these, continuous fiber reinforced additive manufacturing type of systems, and getting that performance. But for additive manufacturing, anybody that's ever done any 3D printing, even at home on your kits or whatever it may be, what we really care about is, can we actually print something? And especially, you try to go to production, you try to make an aerospace part out of it. You want to make more than one part. You want them to be the same. Could you talk about, what goes into that to make sure, you get the reliability, and then, what are those factors there?
So I think I understand what you're asking. So, the way we achieve reliability is with a high degree of testing and quality control. And, we would like to argue that's what you pay for when you buy Stratasys equipment, FDM equipment. Starting with our filament, we're scanning thousands of times a second. Granted, the data isn't necessarily quite that fine grained, but we're looking at, every spool of filament we sell. We're taking multiple scans per inch of every, half mile to several miles of that material that we're selling, in order to make sure that it is compliant to our specifications. We have a robust quality management system for our aerospace materials in particular, where we're making sure that all the traceability around the process and all the OEM specific, customer specific specs are being met, that then travels with the material to the customer. On the hardware side and on the integration side, we do extensive testing to try to improve our MTBF numbers, if you're familiar with that type of measure, on a variety of different dimensions, not just does the part build or not, but aspects of the hardware. How long does the hardware last? Can we load and unload material? Are the different interfaces between the consumables and the machines reliable and robust? And so the I don't know, the lazy way of answering it is to say that we put a lot of work into making sure that things are as robust as possible. And then where they break down for customers, we do our best to try to make sure that we address those issues going forward and ensure that those things don't happen again. Wherever you can do as much as you want to design the best test plan in the world, but the real world and real customers are going to be the ones who find all the little edge cases that you might have missed. And yeah, I can't really say anything more than that, but that's basically our approach.
That's good. No, that's good. I appreciate that, Victor. Yeah, I appreciate it. Okay, we've got a couple more minutes. And so
if I may piggyback off of what Victor just said,
please,
actually.
go ahead, Luke. Yes, please.
So the main part here in the aerospace world, the keywords we're looking for is qualification, certification, and allowables, right? So once we tie those into the system, that is what we're looking for. So the first step with what was just mentioned, the qualification, that implies proving that it meets the standards. So we test, we look at the standards, we comply with all the standards, we document, we trace, and we validate not just the material, but also the process and everything in between. Once we have that down, we move into certification, which say, okay, now that we know how all of this works and that we can prove that it works every time, we can assure that quality, we can provide approval or request approval from the regulatory bodies, and they will then give a certificate and say, okay, yes, this part conforms to this process, which was qualified, which now means that this can make its way onto an aircraft. So the first step going there between qualification and certification is throughout all that testing, we define what the material property allowables are. And what that means is a lot of testing that gives us the statistically derived values that tell us that a part printed with this equipment or technology or material has this tensile strength, compressive strength, shear strength, fatigue, crack toughness, creep resistance, but also the anisotropy, right? A lot of these parts are very anisotropic. So what does that mean? Do we always have to print it in the same way? And that is part of your allowables throughout all of this. So going through these standards like ASTM, the mill handbook, and complying with all of these requirements for testing gives us a part that we can eventually then bring onto the aircraft.
Right. Yes. Very good point, Whoops. Yes, super important for aerospace, commercial aerospace and defense both. Yes, super important. I will say, after going through some of that myself, the process to develop and, bring a technology to fruition in aerospace, I personally feel very safe whenever I board a commercial, airplane. All these things are vetted so much. So, yeah, I agree with all that. Okay, we've only got about one more minute of our hour, so let me make sure that I put in some of our plugs here. And so I am going to go through and give you guys at least, 1 minute or something to give you some final comments. So hopefully that's okay. We'll go past our hour just a little bit. But thank you guys for tuning in. And so again, this was our kickoff for this Between the Layers virtual panel discussion series. And so this is from the Society of Plastics Engineers Additive Manufacturing chapter. We mentioned to you guys a couple times, we're looking for two-way communication with you. And so look up our LinkedIn page, SPE Additive Manufacturing. We've got a website that you see there. We put out a newsletter every so often. But let us know what you guys want to talk about and want to learn about. We say that we're trying to educate the plastics community about additive manufacturing, 3D printing, and then vice versa. Educating our 3D printing worlds about plastics. So thank you again to Adman Dinsmore for sponsorship for this event. And again, you can reach out to them at their websites there for any of their 3D printing or other specialty engineering type of needs or their capabilities for your needs. 3D Natives has an awesome website. You should go check it out. It's probably the best 3D printing website, on the web. And then Implement AM is a workshop model that's been around for a year or two, a couple years now. If you really want to dive deep into additive manufacturing and how to build parts, whatever it may be, look for one coming close to you soon. So the next one is Penn State, Erie in July, and then Cleveland in October. So keep an eye on those. So again, sorry we're over our time, but I wanted to give each of you guys, each of our three panelists, at least a minute. Could you give us any concluding remarks and let us know, maybe we didn't talk about it, or maybe we did talk about it. Any future trends, what you see this industry going towards, if you have a time machine and you go forward 5 years, 10 years, 15 years, and you see something and you came back, what did you see? And so let's go, Woot, if you could let us know some of your closing remarks.
My closing remarks, I'll bring it back to my education, because I am here. I see what the next generation of engineers is used to, and their first thought is, let's 3D print it for a lot of their projects. So I think that when you look forward 5, 10, 15 years, we won't have to push the technology as much as we have been in the past, because of this new generation that is used to the digital aspects of the technology, that is used to the rapid prototyping and iteration version of it, and because of the polymers that are in development, as Ed and the rest of the panel has mentioned today. The switch from one technology to another is a lot lower than from no technology to additive. So that's kind of where I want to leave it with that. So look at the next generation of engineers, because they're coming with printers already in their dorm rooms.
Mm-hmm. Very good point, Luke. Yeah, that's exciting. Ed, what about you?
I think that's incredibly important to mention. The new mindset of the new generation is going to really facilitate and expedite using 3D printing. I feel like we're going to see polymers begin to replace metal if we can move into these very high performance materials, and that's a wonderful thing from many perspectives, from weight, etc. So I'm very optimistic about the future. I wasn't a few years ago, but now that I see a route to high performance polymers, I'm a born again believer in 3D printing being technologically very, very useful.
Sure. I appreciate that. Yeah, I mean, weight's super important in all aerospace applications, but just thinking about what's going on for space, commercializing space, it takes so much energy to get any weight up off of the ground. So yeah, weight is super important. Victor, any closing remarks?
Yeah, a couple closing thoughts, and this is my personal opinion, not necessarily the thoughts of Stratasys, although I think they align somewhat. Is that as in the past, going back 15, 20 plus years, aerospace was the first general kind of set of industries and companies that kind of brought us out of prototyping, and I think that's going to continue to be the sector that pushes us into, as Ed mentioned, really high performance materials, niche applications, functional materials, which we didn't really talk a lot about today, that have special hybrid composite properties. And at the same time, I think more general manufacturing will continue to increase, and I think the automotive industry will push us to streamline and make things a lot neater than perhaps, let's say, like a lower barrier to entry in terms of complexity than maybe the aerospace industry is willing to tolerate. So I think those will continue to be kind of two big trends we'll see pulling from those different sectors of manufacturing.
Very good. Yep, agreed. Yeah, thank you, Victor. Okay, well, I had pages of stuff that we could have talked about. So there's a lot more discussion that could have happened. And so I'll push it one more time before we close out. Reach out to us on the website or on LinkedIn or whatever it may be. Any questions you have, any further discussion. And so with that, we're already 5 minutes over our time. So I want to be mindful of everyone's time. But we will wrap up the Between the Layers additive manufacturing virtual panel discussion here. Thank you again to our panelists, and thank you again to our sponsors and co-producers. With that, we will conclude. Thank you, everyone.
Thanks very much.